For our fifth and final part of Chapter 7, we're going to use Lewis structures to think about our molecules in 3D, both in terms of their shape and their polarity. Is a molecule overall polar or nonpolar? We'll use the Lewis structure and what we learn about molecular geometry to answer that question by the end of this video. So in this final section, 7.6, we've just drawn Lewis structures on a 2D surface, right? On a screen or on a piece of paper. Right? But what we're sketching out are things that actually exist in 3D. So we want to consider what's happening in the space these molecules are taking up, what's happening in 3 dimensions. And to answer that, we need to consider both bond angles and bond lengths to paint a better picture of what's going on. Okay? The bond length, okay, is the distance between any 2 nuclei, right? Shown right here, 1.21 angstroms, that's the bond length. And we'll be talking about a lot in the next several slides, bond angles. Okay? That's anything that shares a common atom. So 2 things that are bonded to the same atom share a bond angle. In this case, 118 degrees. So let's look at a simple Lewis structure, okay, for a heteronuclear diatomic molecule here. Okay? Now diatomics, anytime we have 2 atoms in a molecule, be it the same or different, they're simple. Okay? They're always just linear, right? Connecting 2 points. It's always done with a line. So diatomic molecules, always linear. Simple geometry to visualize. Okay? The challenge in this chapter comes when we have 3 or more atoms in a molecule. Okay? To consider that 3D framework, we need to use something that's known as VSEPR, valence shell electron pair repulsion theory. Okay? And essentially, what VSEPR tells us is that electrons take up space. Electrons have the same charge, right? They're all negatively charged, and those like charges repel one another. So as a result of that, these locations where the electrons exist want to be as far apart from one another as possible to reduce the degree of their repulsion. And that's what we're thinking about with VSEPR. We're not going to talk about attractions or repulsions between the nuclei. We're just thinking about valence electrons in VSEPR. And these are the geometries that we'll see them adopt, depending on if our center atom is surrounded by 2 other atoms, 3, 4, 5, or 6. Okay. Those are called electron pair geometries: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Okay. Depending on how many groups we have, they want to be as far apart from one another. And they do that by adopting these geometries. It'd be the same thing if we tied balloons together and held them by the little piece that you blow into. Okay? They go as far apart as possible. 2 balloons, 180 degrees apart, linear. 3 balloons, 120 degrees. Okay, but all on the same plane. 4, 5, 6 balloons. Now we're thinking in 3 dimensions here, getting them as far apart as possible. And that's going to lead to 2 types of geometries for us. And there is a difference here. Okay, it's important that you know both. In figures 7.16 through 7.19 in your textbook are really important figures that help explain this. Okay. So we're thinking about the geometry always around 1 center atom, and we can describe both the electron pair geometry and the molecular structure. The electron pair geometry talks about the placement of all of the electron pairs, the bonded electrons and the unshared lone pair electrons, and we treat them all the same. The molecular structure is different. Okay? It describes only the placement of the atoms that are bonded to the molecule. Okay? So it's not talking about the lone pairs. They get treated differently. Now there is a situation where they'll be the same. Okay? If a center atom doesn't have any lone pairs, then there's nothing to be treated differently. So the electron pair geometry and the molecular structure are the same. And that's what we're going to think about first. And the more challenging ones will come after, where our center atom does have lone pairs and they're no longer the same. Okay. So to describe electron pair geometries and molecular structures, we'll use something that's known as the Ax notation. Okay, and you'll notice these slides are pulled from outside of the Openstax textbook. Okay, the Ax notation. Okay. A in the Ax notation is our center atom. Okay. X is describing a terminal atom, so all the things on the outside. And notice it says atom, not bond. Okay, so a double bond, a triple bond, both just count as one because they're just going to one atom. And then E in the Ax notation describes a lone pair. So let's look at our linear configuration. Okay. If we have one center atom, two terminal atoms, we call that AX2. Because remember, we're not thinking about anything with lone pairs to start, so there's no E in the Ax notation. So A, it's always just A, one center atom. X2 tells me two terminal atoms. And we call that molecular structure and electron pair geometry linear. The bond angle is 180 degrees. We only see this in things that are electron deficient, okay? Because if they only have two groups and no lone pairs, they can't satisfy the octet rule. We see that here, and we see it in the next one as well, where we have three terminal atoms. So now we're looking at AX3. We call that trigonal planar. That is where our terminal atoms are all in the same plane, hence trigonal planar, and they're pointing at the corners of an equilateral triangle. So they are all 120 degrees apart. And because I have three bonds to my center atom and still no lone pairs, I continue to be electron deficient. We see these with boron. Moving to our next notation, though, this is the one that we see really commonly because it's the one that carbon likes to have. 4 electron pairs around our center atom, AX4. That molecular structure is called tetrahedral because the terminal atoms are pointed at the corners of a tetrahedron, thinking about like a three-dimensional pyramid. The bond angle between any of these two is 109.5, and our center atom is happy with an octet now. Okay. So for each of these, as we go through them, you should know the Ax notation, know the name it corresponds to, right, tetrahedral in this case, and know the bond angle. What about for 5? Okay. Because we described in the previous video, these are possible. 5 bonds mean we've exceeded the octet, but there are things that are hypervalent, right? Phosphorus is an example here. AX5 is called trigonal bipyramid or trigonal bipyramidal because it's describing 2 triangular pyramids fused together base to base, where these 3 make up the base, and we have a triangle pointing up and a triangle pointing down. 2 types of bond angles here. The ones in the middle are 120 degrees apart, right? So 120 degrees right here or between these two, just like we saw with trigonal planar. Okay? But if I take one of these top or bottom ones plus a middle one, they're 90 degrees apart. And these have to be hypervalent. So AX5, trigonal bipyramidal, a couple of different bond angles there. Our last one is AX6, which again is hypervalent, shown here with sulfur. Okay. AX6 is called octahedral, and this is 2 pyramids with a square base fused together. All the bond angles here are 90 degrees, right? 90 degrees there, 90 degrees there, 90 degrees going down. Unless you choose 2 things that are trans to one another, then we could say they're 180 degrees, right? A couple of straight lines in there. So those were the situations where we didn't have any lone pairs to worry about, okay? Know the notations, know the names. But now we're going to think about when the center atom does have lone pairs, because now the electron pair geometry and the molecular structure are not the same. They're different things, because when we have those lone pairs, they cause deviations from our ideal bond angles. The reason for that is because lone pairs of electrons take up extra space. Okay? Lone pairs repel one another more strongly than do bonds. So lone pair repulsion is the strongest, followed by lone pair repelling a bond, and lastly two bonds repelling one another, which is effectively what this slide is saying. We see that if we look at ammonia, for example. Okay? We just saw methane used as an example, AX4, okay, bond angle of 109.5. But when I switch to ammonia, put nitrogen in the middle there, and one of those bonds becomes a lone pair, which you see up top, then my bond angle shrinks to 107 because that electron lone pair is taking up more space. That's what's shown up on the top there in the middle in blue. If I introduce a second lone pair like water has, then it shrinks even further, down to 105. Okay? Those lone pairs have a stronger force of repulsion. Okay? And we've already talked about hypervalent. We've already talked about hypervalent molecules. Okay? Lone pairs are on the center atom, and that will affect our shape. Another thing that can affect our bond angle are if we have higher order bonds. Okay? Double bonds, which are made up of 4 electrons, and triple bonds made up of 6 electrons, more electron density occupy more space, and they repel more strongly than would a single bond. Not quite as strongly as a lone pair, but if we're thinking about forces of repulsion, a lone pair is highest, followed by a triple bond, followed by a double bond, and lastly, a single bond. Now, any deviations from the bond angle, you will never have to memorize what the specific bond angle is, right? Like the 107 in ammonia. Just know that if we have lone pairs or higher order bonds, it makes the bond angle for everything that's left smaller, which is what's shown in this slide right here. Okay. So now, if we've got lone pairs and we're trying to determine the structure with valence shell electron pair repulsion, we first draw the Lewis structure, make sure that's perfect, right? Draw the Lewis structure, make sure you use all your electrons, happy octets, happy formal charges. Then take your center atom, figure out how many lone pairs are on it, if any, and how many bonds are going to it. Keeping in mind that a lone pair, single bond, double bond, triple bond all count as one region of electron density. Then we identify the electron pair geometry. Then we consider if it's different or not. Okay, if there's no lone pairs, the electron pair geometry is equal to the molecular geometry. But if there are lone pairs, then they're different. And that's what that point number 4 is talking about, deviations from the ideal bond angle, right? Molecular structure will be different if we have lone pairs. And the names of all of those molecular geometries are shown on this table here. So the strategy that I recommend you take, right, is figuring out the electron pair geometry. I kind of call that the family for these things. And then if they're lone pairs, how many? And then what member of the family does that take us to? So we will start by looking at the trigonal planar family. Okay, there's nothing left with linear because we'll never have one bond and one lone pair. But I can go down to trigonal planar here. Okay, I can swap one of those for a lone pair. Okay. So now I've gone from AX3 to AX2E. Okay. This is telling me A, one center atom, X2, 2 terminal atoms, E, and then it's 1 that's implied but not shown, 1 lone pair. This we saw before. This is called trigonal planar. AX2E is called bent. Okay? And notice as we go to these other family members, all of the subscripts here, remember we've got 1s that are implied but not shown, the subscripts between the X's and the E's add up to the family member. And you can never have more E's than you do X's. How about tetrahedral? we can go to AX4. Okay. Tetrahedral, we saw that before. AX3E1. Okay, swap one atom for a lone pair. This is called trigonal pyramidal. AX2E2. That again is called bent. Trigonal bipyramidal family. Okay. AX5 we saw before. AX4E1 has a fun name. It's called seesaw. AX3E2 called T-shaped. And then AX2E3 called linear. I said just a second ago you can't have more E's than you do X's because I forgot about this form of linear. This is the only situation where you have an excess of E's. A better rule would be you can never go to just AX1. We finish off with the octahedral family. We saw AX6 before being called octahedral. If we swap one of those for a lone pair, and that's called AX5E1, square pyramidal, because it's a pyramid with a square base. And then AX4E2 is square planar. Okay. The table that we started with right here shows two more members of that family. They're exceptionally uncommon, so I'm not going to include those deliberately on this slide. A couple of things to look out for. In our trigonal bipyramidal and our octahedral families, right, we've got to be careful where we're putting those lone pairs. In the trigonal bipyramidal family, your lone pairs go in what's known as the equatorial position, right? Think about those like the equator here in the middle. That's where you put your lone pairs. Notice that's where the things are falling out of and being replaced. But in the octahedral family, we replace the axial atoms with lone pairs. Okay. So just be on the lookout for that. Plenty of examples in your book for practice. Including one right here. You can practice drawing the Lewis structure for ClF3. Get the molecular structure and then the electron pair geometry. Pause the video, give that one a shot. Your electron pair geometry is trigonal bipyramidal. Your molecular structure for ClF3 is T-shaped. Okay. Another one, okay, tying together a couple ideas, is to draw the Lewis structure of ozone, O3. Okay. That's really good practice as well. There are two resonance contributors of ozone. The electron pair geometry is trigonal planar. The molecular geometry is bent. So you can try that one for practice as well. One last question is, well, what if there are multiple centers simultaneously, right? I could be asked about anything here, you know, carbon, nitrogen, oxygen. But in this course, we're only going to consider the geometry of one center atom at a time. So if you've got higher molecules like this, I will ask you specific atoms to determine the geometry about. We now use those ideas to discuss molecular polarity and dipole moment. Yet again, we saw this at the beginning of the chapter with electronegativity. Remember, if we have a polar bond, electrons are pulled towards whatever is more electronegative. That gives us a separation of charge and results in an overall dipole moment, which is calculated with this equation. You'll not be asked to use that in this course. But you will be asked to recognize where dipole moments exist. Okay? Previously, we represented those with a delta positive and a delta negative. But we can also represent the dipole moment as a vector. Okay? So it has a direction and a magnitude. So anytime you see an arrow like this, right, an arrow with that little cross at the end, that's showing you that you have a dipole vector, and it points toward whatever is more electronegative. So we know polar bonds exist, but the question we're solving here at the end of the chapter is a molecule overall polar? Do we have a molecular dipole moment? Because it's possible to have polar bonds but be a nonpolar molecule. Okay. Now, a molecule is polar only if it has both a positive pole and a negative pole. So one part that's partial positive and one part that's partial negative. If it's a nonpolar molecule, there's no dipole at all. Okay. Now, diatomics are simple because the bond itself effectively represents the molecule. So if you have a polar bond in a diatomic, then you have a polar molecule. If you have a nonpolar bond in a diatomic, it's a nonpolar molecule. Simple. But for everything we've seen in this video with 3 or more atoms, right, we've got more criteria to satisfy. Yeah, we have to have polar bonds, right? If we don't have any polar bonds, it's impossible for a molecule to be polar. But not only do we have to have polar bonds, we have to have the right kind of geometry to have an overall dipole moment. So we need to consider, do those molecular dipoles, those vectors, cancel one another or not? Okay. So we have to think about geometry when determining dipole moment, because we have to look out for if those dipoles cancel one another out. So let's look at an example here. Okay. CO2 and H2O. Both of them contain polar bonds. Okay? Oxygen is more electronegative than carbon. Oxygen is more electronegative than hydrogen. So in both situations, oxygen's pulling the electrons towards it. But CO2 has an AX2 notation. It's linear. So while it has polar bonds, those vectors have canceled one another out, right? It's like tug of war going in the equal opposite direction. There's no movement. There's no overall dipole because they've canceled one another out. But H2O here, these are both being pulled upward. H2O is an AX2E2 notation if you draw out that Lewis structure and look at the center atom. So its geometry is bent. These dipoles don't cancel one another out. There's an overall molecular dipole. So both of them have polar bonds, yes, but this is a nonpolar molecule. This is a polar molecule. A couple more examples shown on this slide. Okay, XeF4, nonpolar molecule. ClF3, the T-shaped one we saw before. Okay, these two fluorines cancel one another out, but there's nobody canceling out this fluorine. So there's an overall molecular dipole moment. We wrap up with a couple example questions. Okay. First one, drawing a Lewis structure for a polyatomic ion to say, does carbonate have an overall molecular dipole? So pause the video and sketch out that Lewis structure. Try and answer this question. Once you've drawn that structure, you'll see that the Lewis structure of carbonate, well, first has 3 resonance contributors. So hopefully you paid attention to the resonance. And then you have to remember what resonance means, right? That double bond that's shared between 3 oxygens doesn't ever really exist as a double bond. So all of those carbon-oxygen bonds are the same. We have a trigonal planar, right, AX3 geometry, and all of the vectors are canceling one another out. So even though CO3 has the charge right there, 2 minus, right, it's a non-polar molecule, polyatomic ion in this situation. Okay. There are a couple Lewis structures that I've added at the end here for practice. Okay, you can try these on your own time and search the answers afterward. Lots of key ideas to pull out of this chapter. Certainly know electronegativity, the difference between ionic covalent, Lewis structures, resonance, formal charge, molecular structures, electron pair geometries, and here at the end, molecular dipoles. Practice makes perfect when it comes to chapter 7.